welcome to this video. I am back. I am Piyush Kumar Kamlesh, Faculty of Physics, Jaipur National University, Jaipur. In the last lecture, we have studied about the interference, what is interference, and we have also seen Young's double slit experiment. Now, I discussed the outcomes of Young's double slit experiment, what we got there. We calculated the resultant amplitude of two waves, that was A1 is square plus A2 is square plus 2 A1 A2 cos phi. This phi is the phase difference between two initial waves, and A1 A2 are those amplitudes. We also discussed about the intensity of the resultant wave, that was I equal to I1 plus I2 plus 2 is square root of I1 I2 cos phi. This was the resultant intensity after during the superimposition of the waves. We also discussed maximum and minimum intensities. We discussed that when both the amplitudes are not equal, means A1 is not equal to A2, then maximum intensity was I maximum was I1 is square root of I1 plus square root of I2 ka whole square, and the minimum intensity I minimum, it was square root of I1 minus square root of I2 whole square, and this was when A1 is not equal to A2, both the amplitudes are not same. We also discussed in the last lecture, then when both the waves have same amplitude, A1 equal to A2, suppose it is equal to A, then we have I maximum equal to 4I, or I maximum equal to 4I, or how much? When we put A1 equal to A2, it will provide I1 is equal to I2, right? So, square root of I1 and square root of I2 whole square will give you 4I. In terms of amplitude, we can write it as 4A square. Similarly, the minimum intensity, what will be the minimum intensity? Square root of I1 minus square root of I2. So, since I1 is equal to I2 and we are saying it I here, then square root of I1 minus square root of I2 will be 0. So, minimum intensity was 0. I repeat here, the maximum intensity in the case when both the amplitudes are not same will be square of square root of I1 plus square root of I2, and minimum intensity is the square root of I1 minus square root of I2. And when both the amplitudes are same, maximum intensity is maximum 4A square or 4I, and minimum intensity is 0. The condition of getting maximum intensity was phase difference must be even multiple of pi, right? You remember this, where n is equal to 0, 1, 2 and so on. And the condition for getting minimum intensity is phase difference between the two waves must be odd multiple of pi. Here again, n equal to 0, 1, 2, 3 and so on, natural numbers. Okay, so these two are the conditions for getting maximum intensity as well as minimum intensity. Okay, on the behalf of these two conditions, we can calculate the conditions in terms of path length. Fine. If we calculate path length, then we know that relation between phase difference and path difference. The relation between phase difference and path difference is phase difference is equal to 2 pi by lambda into path difference delta. Okay, so for maximum intensity, here delta will be lambda upon 2 pi into phase difference. So when we put phi equal to 2 and pi, so here from here we will get for maximum intensity we have phase difference equal to 2 and pi. So what will be the path difference? It will be lambda upon 2 pi into 2n pi. Pi to pi cancel, 2 to 2 cancel, we will get here delta is equal to n lambda, or we can write it as it is even multiple of half wavelength, right? So this is the path difference. This is the condition of path difference for maximum intensity. Similarly, for minimum intensity, we know that phi is odd multiple of half wavelength. Odd multiple of pi. So if we calculate the path difference for minimum intensity, it will be delta is equal to lambda upon 2 pi into 2n plus 1 pi. So pi to pi cancel. From here we will get delta is equal to 2n plus 1 lambda by 2. Means for minimum intensity, or you can say for destructive interference, we get odd multiple of half wavelength, and for maximum intensity, or you can say for constructive interference, we get path difference is even multiple of half wavelength. This is the only difference. It is for constructive interference and it is for destructive interference. So at those point of the screen at which we are getting maximum intensity, there the phenomenon which is happening is constructive interference, and at the remaining points at which we get darkness or we get minimum intensity, at those points we are getting destructive interference, right? So this is the matter which we studied in the last lecture. Now we will solve some problems based on these formulation. Okay, you have to given ratio of intensities of two waves intensities of two waves is 16:1. Ratio of intensities of two waves is 16:1. Calculate the ratio of the maximum and minimum intensities during superposition. So we have two waves having ratio of their intensity 16:1, and when they superimpose, we have to calculate the intensity and the ratio of maximum and minimum intensities. So from the Young's double slit experiment, we know that the maximum intensity I maximum is square root of I1 plus square root of I2. This is the maximum intensity, and minimum intensity is I minimum equal to square root of I1 minus square root of I2 whole square. So the ratio between maximum intensity and minimum intensities will be I maximum upon I minimum equal to this upon this. Now here given is I1 upon I2 is equal to 16/1. So from here we will get square root of I1. On taking square root on both sides, we will get square root of I1 upon square root of I2 is equal to 4/1. Square root of 16 is 4, square root of 1 is 1. Okay. So to calculate the ratio between maximum and minimum intensities, we will divide in the right hand side denominator and numerator both by square root of I2. So we will get, when we divide square root of I2 inside this equation, or you can say we will divide by I2 in both numerator and denominator, we will get here square root of I1 upon square root of I2 plus 1 square divided by square root of I1 upon square root of I2 minus 1 whole square. Okay. So here we know that square root of I1 upon square root of I2 is 4 upon 1, or you can say 4, it is 4. We will put these values here. So I am removing this question. What will we get here? I maximum upon I minimum is 4 plus 1 square upon 4 minus 1 square. So it will be 25. 4 plus 1 is 5, square is 25, 4 minus 1 is 3, square is 9. I maximum upon I minimum. So we have to ask here, I maximum is to I minimum, it is now 25:1. This is the required ratio. So the simple questions will be asked. We can solve this on the direct formula basis. You can try some more problems. One more problem we will solve here, and it will be for the resultant amplitude of both the waves during superimposition. Suppose there are two waves having amplitude 1.0 and 2.0 units, having amplitude 1.0 and 2.0 units, then and interfere at some point. At some point. And the phase difference between these two waves is 60 degree. Then the question is, what will be the resultant amplitude? What will be the resultant amplitude during superposition? Here you have to give in the amplitudes of both the waves, 1.0 and 2.0 units, and the phase difference between these two waves also given. You have to find out the resultant amplitude. We know the formula for resultant amplitude is R is equal to square root of A1 square plus A2 square plus 2A1 A2 cos phi. Here A1 and A2 are the amplitudes of two waves and phi is the phase difference. Here we have to give, the given here A1 is equal to 1 unit and A2 is equal to 2 units. Suppose A1 is 1, A2 is 2, then this R will be 1 square 1 plus 2 square 4 plus 2 into 1 into 2, kitna? 2 to the 4 cos phi. Cos phi is cos 60 degree. Cos 60 is how much? Cos 60 is 1 by 2. So when we put cos 60 1 by 2, then we will get here 2. So 2 plus 4 6 plus 1 7 is square root of 7. This is the resultant amplitude units. Right? Okay. So these type of questions may be asked in the examinations, or these are actually the basic questions. We can practice for more questions having some complicated situations. So you can practice some more questions by your notebooks, by your books. Now we will discuss the next topic that was based on the division of wavefront and division of amplitude. Means the next examples, next we will see the examples of interference produced by two phenomena. We have also discussed one thing, that how can we produce two coherent sources. So I discussed there in the last lecture that we can produce two coherent sources by two ways. The first one is production of coherent sources. Since two independent sources cannot be coherent, so we have to produce them. Okay, so there are two methods. These are methods of production of two coherent sources. Number one, division of amplitude. Number two, division of wavefront. In division of amplitude, we have a source, common source for both the coherent sources. If we are producing here two coherent sources, okay, so a light comes fall on the screen, and fall on a screen, and that splits into two parts. Okay, so when a light beam is split into two parts, then the intensity of both the parts will be decreased. Okay, so we get two coherent sources of decreased amplitude, you can say, है ना? And in division of wavefront, we produce two coherent sources by a single source. They have same amplitude. Okay, so in division of wavefront, we have both the coherent sources having same intensities, but in the division of amplitude, we do not have sources of same amplitude. So the intensities may vary, and due to variation in the intensities of the individual waves, we will not have the sharp interference pattern. There are some conditions of good interference pattern. We will also study the conditions of good interference. Condition of good interference. Number one, the first condition is both the sources have same frequency. Both the sources should have same frequency. What will happen if the frequency is different? If we have two sources having different frequencies, then their maxima and minima will change continuously with respect to time. So the pattern will not be fine. Suppose at some time you are getting maxima at this point, next maxima is at this point, next maxima is at this point, and minima are somewhere in the middle of these maximas. Then if we have two sources of different frequencies, then these maxima will travel with respect to time. At some moment these are at this place, at another moment these may come to this place. So at the screen the maxima and minima will travel. So we will have two sources of same frequencies for good interference pattern. Second, the phase difference must be either 0 or constant. The phase difference between two sources must be 0 or constant. If this is not 0 or not constant, that means if the phase difference between two waves varies, then there will be no interference pattern. Okay. Next is when we have two sources. Then the separation between these sources separation between two sources must be small. कम होना चाहिए. It must be minimum. If we have greater separation or large separation between two coherent sources, then what will happen? That when two rays reaching at the screen will have larger path difference, and due to large path difference, the separation between two consecutive maxima or two consecutive minima will be minimum, or it will be decreased enough. So we cannot detect maxima and minima, very sharp maxima and minima. There will be very less difference. So it must be minimum so that we can get distinct maxima and minima. Also, the separation between sources and screen must not be large. The sources by which we are getting interference pattern, or we are producing interference pattern, and the screen at which we are getting interference pattern, they must not have large difference. Okay, so the both sources have same frequency, phase difference either must be 0 or must be constant, and separation between two sources must be small. Also, we must have the amplitude of, for it is actually for sharp maxima and minima, the amplitudes of both the waves must be equal. What will happen if the amplitudes are not same? We will not get complete darkness at the place of minima. So when we will not have complete darkness at the place of minima, then there will be then the maxima will not be sharp enough. Okay, it will not be that much bright, that much it should. So amplitudes of both the waves must be equal. If this is, then maxima will be of maximum intensity and minima will be of zero intensity. So these are some points which we should consider for good interference pattern. Now we will see an example for the phenomenon of interference which is produced by the division of amplitude, and that is thin film interference. We generally see in our daily life this phenomenon, thin film interference. Suppose you have a thin film, you can say it is the film of water or it is the film of soap bubble. It has a thickness T and its refractive index is mu. Okay, suppose a light beam incident at this point here. This is beam A, B, and this is the normal to this point. At this point of this film, this beam splits into two parts. It will partially reflect and it will partially transmit. So suppose this is the angle of incidence I, then it will reflect in this direction at the same angle. This is the law of reflection, and it will partially transmit. Since this mu is greater than 1, so it will bend towards the normal because it is the denser medium comparatively to the air. This is the first medium, this is the second medium, this is the third medium. First medium is air, second medium is that film medium, and third medium is also air. So when a beam AB incident on this thin film at point B, it partially reflects in the direction this BC and partially transmit in the direction BD. This is point D. At point D, it again partially reflect and partially transmit. This is the normal. Suppose the angle of transmission is R. So this angle will again R. Now at point D, it partially reflects and partially transmit. Reflect in the direction DE, transmit in the direction DF. Okay, this angle of reflection is R and this angle is I, the angle which is same. At point E again it will, this is the normal, suppose this is the angle R, this point is E. Again at this point it will partially transmit and partially reflect. This angle is again R, and here again also this phenomenon will continue till the end of this beam. रुकना है 3 minutes है. Okay. Now here it will again partially transmit and partially reflect. So this phenomenon will go on. So we have to study here how the interference pattern produce in this film. मैं 1 मिनट का ब्रेक ले लेता हूँ, फिर इसको दोबारा स्टार्ट करेंगे क्योंकि कम से कम 10-15 मिनट लगेंगे. This reflected beam DE again splits into 2 parts. The transmitted part, it is suppose EG, and the reflected part it is suppose EH. Again it is transmitted I and will reflect in some other direction. Okay, so to calculate the conditions of interference pattern, that at what point we will get the maxima and at what point we will get the minima, we will have to draw a normal from point D on BE. This is some geometrical preparation we are doing here. Suppose it is point J, and we will again draw a normal from point E to point BC. This is the normal. Okay, this angle was I and this point is K. This point is K. Okay, by drawing this normal, what we do, that the path of these 2 beams KC and EG will be equal, and before that this path BK is the extra path. Okay, so to calculate the condition of maxima and minima, we have to calculate the path difference between 2 beams. So here is a common beam. There are 2 systems actually. The upper system is called reflected system, in which the beam comes from an external light source in the direction AB, and this reflected in direction BC. Again this beam is here, so we will call it reflected system, and the other one is transmitted system, in which we are getting 2 beams DF and HI. This third region is transmitted system and the first region is reflected system. So now we here calculate the thin film interference in reflected system. However, the approach for calculating the conditions of maxima and minimum in the transmitted system will also be the same. Okay, so in reflected system, here the beams are A, this BC beam, path of BC beam is A, B, C, and path of EG beam is A, B, D, E, G. Okay, this is the full path of this beam. So the net path difference between these 2 beams will be how much? This is the path BD plus DE, which this second beam EG travel extra from the first beam. So the path difference between 2 beams BC and EG is how much? delta is equal to BD plus DE. BD plus DE. This is path in the film. This path is traveled by the second beam in the film. And this is the path BK. This path is traveled extra by beam 1 or beam BC. This is the extra part traveled by this beam, because from K onwards, KC and EG are same. So this is the extra part, so we will subtract it, and this path is in the air. Since both the paths are traveled in the different media, so we cannot add or subtract these. We have to convert in the same medium. So we know the formula that path, I will write it here, path in the air is equal to mu times the path in the film. Or path in the medium. So this is the path BD plus DE travel in the medium. We can convert it equivalent path of air. So it will be, now the path difference will be delta equal to BD plus DE into mu. Now this is the path which is equivalent to the path in air minus BK. So this is the net path difference between these two beams. If we calculate BD, DE and BK, then we can calculate the path difference between these two beams. We will calculate BD, DE and BK by this geometry. Now we see the triangle BDJ. In triangle BDJ, we know that this angle is R. Okay, we have to find out BD, this length, and we know the thickness of the film is T, means we know the path DJ, this width we know DJ, and this angle we know. If we know this angle R, then this will be the base, this will be the hypotenuse, and this will be the perpendicular. So we know that the relation between base and hypotenuse is cos, given by cosine. So cos R is equal to base upon hypotenuse dj upon BD. So BD will be dj upon cos R. dj is how much? T. It is T upon cos R. Similarly, we can calculate DE. In triangle, or you can say that both of these triangle BDJ and triangle EDJ are congruent. So this line will be equal to this line, and this line will be equal to this line. When you know the condition of congruent triangles, minimum 3 parameters will be the same. So we know here that this angle is equal to this angle, and this line is common in both the triangles. Also, this is the 90-degree angle, this is the 90-degree angle in both the triangles. So 3 parameters are same, then we can say that these triangles will be congruent, means rest of the 3 parameters will also be the same. In a triangle, there are actually 6 parameters, 3 angles and 3 sides. So on being the same of these the 3 parameters, the rest of 3 parameters will be same. Hence we will get BD equal to DE. So DE is equal to BD, and it is again equal to T upon cos R. We will give some equation number. The equation for this path difference formula is 1. For BJ, sorry, it is BD. It is equation number 2, and DE equation number 3. So now we have the value of BD, we have the value of DE, but BK is still unknown. BK is this distance. To calculate this distance, we only know this angle, angle KBE, because this angle is I, so angle KBE will be 90 minus I, okay, and nothing else, right? We don't know either BJ or JE or BE, okay. So to calculate BK, we again use these two triangles, triangle BDJ and triangle EDJ, to calculate BJ and JE. When we will calculate BJ and JE, then we will have two known parameters, one this angle KBE, and one this parameter BE. On knowing these two parameters, we can calculate BK, okay. So again, in this triangle BDJ, we should write our results here. BD equal to DE equal to T upon cos R. Okay, so in triangle BDJ, we have to find out BJ. So this is the angle, the opposite side is perpendicular, and we know perpendicular we have to calculate, okay, and we know this base dj, this is equal to t, so we will put here the formula tan r. Tan r is perpendicular upon base, perpendicular is bj, base is dj. So bj equal to dj tan r, or you can say bj equal to t tan r, because dj is equal to t. Again, since these two triangles are congruent, so this portion bj is equal to je, so je is equal to bj and it is equal to t tan r. So what will be be? BE will be BJ plus JE, means 2T tan R. This is equation number 4. So from equation 1, 2, 3 and 4, we can have the value of delta is equal to mu BD plus DE, T upon cos R plus T upon cos R, minus BK. Okay, BK is still unknown, sorry. So in this triangle, we will write here after some time. Now in triangle KBE, we know this angle is I, so the remaining angle will be 90 minus I, since this angle is 90 degree. We draw a perpendicular here, okay, so this will be, since this is also a normal here, so this is I, since this is I, it will be 90 minus I. So cos 90 minus I this angle is 90 minus I. Cos 90 minus I is equal to, cos is base upon hypotenuse, so base is BE, hypotenuse is, sorry, base is BK and hypotenuse is BE, BK upon BE. So BK is BE into cos 90 minus I is sin I, sin I, fine. So we have BK equal to, BE is how much? BE is 2T tan R, 2T tan r into sin I. Sin I. It is equation number 5. So now from equations 1, 2, 3 and 5, we have delta equal to mu BD plus DE. BD and DE are T upon cos R. So it will be T upon cos R plus T upon cos R minus BK. BK is 2T tan R sin I. Now I am removing this diagram, and we have this sin I is here. We have this expression. On solving, we will get is 2 mu T upon cos R minus 2T sin I tan R. From Snell's law, we know that mu equal to sin I upon sin R. Okay, so when we put the value of sin I, we will get from here sin I equal to mu sin R. So from Snell's law, we hear mu equal to sin I upon sin R. So sin I will be mu sin R. We will put the value of sin I here. It will be 2 mu T upon cos R minus 2T. Sin I is mu sin R, mu sin R. Tan R is sin R upon cos R. Okay, so this sin R into sin R, it will be sin square R, and this upon cos R is in both the terms, first term and second term. We will take it common. Also 2 mu T is here also and is here also. So we will take common these two terms. We will get delta is equal to 2 mu T upon cos R. It is common in both the terms. So from first term the remaining is 1, and in second term remaining is sin square R. Sin square R. 1 minus sin square R is cos square R. Cos square R is in numerator, cos R is in denominator. So it will be delta equal to 2 mu T cos R. It is the path difference between the two beams in the reflected system. Also one thing which we have to mention here, that by the laws of reflection, when a beam reflected through a denser medium, it get an additional path difference of lambda by 2. So this was the reflected system, upper system. Okay, when the first beam, when the beam comes at point B and reflected from here, it is now reflecting from the denser medium. So it will get an additional path difference of lambda by 2. However, the second beam is like this. It is first transmitted, then reflected, because since this is the rarer medium, so it is reflecting here from rarer medium, so no additional path difference will be here. And at this point it is transmitting here, so no additional path difference will appear here. So only the additional path difference will appear in the path of the first reflected beam. We will put it here. In addition, we can write it as due to the reflection of first beam from denser medium an additional path difference of lambda by 2 will appear. So the net path difference between the two beams in reflected system will be delta equal to 2 mu T cos R plus lambda by 2. This is the net path difference. We know the conditions of maxima and minima. For maxima, path difference must be even multiple of half wavelength, means n lambda. So the condition of maxima will be, what is the value of delta here? 2 mu t cos r plus lambda by 2. This is delta and it must be equal to n lambda. When we replace this lambda from left side to right side, we will get 2 mu t cos r is equal to n lambda minus lambda by 2, or 2n minus 1 lambda by 2, 2 mu t cos r. This is the condition for maxima in thin film interference in reflected system. Similarly, we can calculate the condition for minima. For minima, this path difference is odd multiple of path, half wavelength. So for minima, it is odd multiple of half wavelength, 2n plus 1 lambda by 2. It is 2 mu t cos r plus lambda by 2 is equal to, when we expand this bracket, we will get n lambda plus lambda by 2. Lambda by 2 cancel. The condition of minima, we get 2 mu t cos r equal to n lambda. So these two were the conditions of maxima and minima in thin film interference in reflected system. Thank you so much for watching this video. In next, we will discuss thin film interference in the transmitted system and why an extended source is necessary for this interference. Thank you.